Welcome to Yaka Digital Network videos. If you've ever looked inside a broken radio or charger, those tiny metal parts and green boards can look completely overwhelming. To understand them, it helps to imagine that inside every electronic device is a fast-paced, bustling city. Think about a busy Kampala taxi park at rush hour. Without people and rules to manage the movement, it's just chaos. A circuit board is organized the same way. It relies on specific parts, called components, to direct the flow of electricity so it goes exactly where it needs to go. Learning the specific jobs these components do allows you to read any circuit like a map. It means you can start fixing real-world devices, like your family's radio, all on your own. Electronic circuits are organized pathways of energy, built on simple community roles that work together to complete a task. We can divide these parts into two main groups. The first are passive components, such as resistors. You can think of these like the speed bumps on the Entebbe road. They affect the flow of electricity by slowing down whatever hits them. This diagram shows a resistor limiting the flow of electricity. While passive components manage energy, they have a major limitation. They cannot make decisions or change their behavior based on a signal from the outside. Active components, like transistors, are different. Instead of a speed bump, imagine a Kampala traffic police officer standing in the middle of a busy junction, actively deciding which cars move and which stop based on the traffic levels. This graphic demonstrates how a transistor acts as a gate. It only opens the main electrical pathway when a secondary signal arrives to trigger it. Because they can switch or boost current, these active components act as the brains of a circuit. Active components provide the logic needed to process information, turning a simple path for electricity into a system that reacts to its surroundings. Let's use this logic to solve a community problem. Imagine you are designing a security light for a shop in Barara that needs to turn on automatically at sunset without anyone needing to flip a manual switch. To do this, we need a part that can sense the environment. We use a light-dependent resistor, or LDR. Think of it like a traditional night watchman who only opens the gate once the sun finally goes down. This chart shows how an LDR works. Notice the bar graph next to the symbol. As the amount of light in the room drops, the LDR's electrical resistance shoots up. This change creates a signal we can use to trigger an action. But that signal is too weak to turn on a bulb alone, so it travels to the transistor. As the schematic expands, you can see how the LDR signal triggers the transistor's main gate to switch on. Combining a passive sensor with an active controller creates an automatic if-then system. If it gets dark, then the circuit sends power to the light. However, the transistor is a small part. It isn't strong enough to handle the heavy power needed for a bright outdoor security bulb. Our brain needs some muscle to finish the job. We add a relay. Think of it like a village chief giving an order to a construction crew. The transistor's small signal activates the relay, magnetically snapping closed a thicker wire carrying high-voltage power to the bulb. Before you permanently connect these parts, you must follow the professional engineering process and build a test version. Engineers use a tool called a breadboard for this. It's like the scaffolding used when building a house in Wandegia. It holds the LBR, transistor, and relay securely in place for testing without requiring any permanent glue. Testing on a breadboard allows you to verify your logic and fix any mistakes before you commit to building the circuit for real. Once our test light in Mbara works correctly, we have a proven design. As the light levels drop, the components fire in sequence and the security light illuminates exactly as planned. Now we move the parts to a permanent board using a process called soldering. By using a hot tool to melt metal, we fix the components into place. It's like using a strong local resin to permanently fix a handle onto a clay pot. To do this correctly, always use flux, a special paste that helps the metal flow, and keep your iron tip clean. This prevents cold solder joints, which are dull, weak connections that stop electricity from flowing and cause the circuit to fail. Mastering this skill bridges the gap between a theoretical idea and a durable, finished product that can survive the elements in the real world. The same logic used to build this security light is what you use to troubleshoot and repair broken electronics throughout your community. To find these faults, you use a tool called a multimeter. Think of it like a measuring scale used for matoke in the market, but for electricity instead of weight. It allows you to logically check for specific problems like a broken connection or a part put in backward. These O-level skills are a pathway to self-reliance. They allow you to start a small business in your own village, repairing solar lanterns and phone chargers for your neighbors and friends. These technical skills provide the foundation for building and repairing the essential tools your neighbors rely on every day. You can watch more videos for all classes here and get all content at www.yaka.cc.